In this HVAC training video, we're going over 4 examples on how to check the refrigerant charge. So we're measuring the pressures and temperatures on a single speed air conditioning system with a thermostatic expansion valve in order to determine if it's undercharged, correctly charged, or overcharged. This is an R410A unit. Because the system has a thermostatic expansion valve, we're going to be using the subcooling method, and we need to take our measurements and compare that to the rating plate on the outdoor unit. Before measuring the refrigerant charge, it has to be at least 70 degrees inside and 70 degrees outside or above. We need to let the unit run for 5 to 10 minutes, and we have to have good airflow across the indoor coil. So we're talking about around 400 CFMs per ton of air conditioning. So let's assume we've had this system running now for 5 to 10 minutes. Our gauges and temp probes are all attached, and I'm going to run you through this scenario. So we have the red high side gauge attached to the small liquid line of the outdoor unit, and we're measuring a pressure of 346 psi. We convert that to a saturated temperature for R410A of 106 degrees, and that's the temperature of the refrigerant as it's flowing in the middle of the outdoor coil. Now, as the refrigerant flows through that coil and exits the outdoor unit, we're also measuring a temperature on that small liquid line. And so with our temperature reader, we have 96 degrees on that small liquid line. And so what we do to determine the subcooling, the actual subcooling, is 106 degrees minus 96 degrees, and we're left with 10 degrees of actual subcooling. We're going to take that actual subcooling, we're going to compare that to the target subcooling listed on the outdoor unit rating plate, and in this scenario, the target subcooling is 11 degrees. So if the target subcooling is 11 and the actual subcooling is 10, we have an accurate charge for this system because we need to have an actual subcooling that's within plus or minus 3 degrees of the target subcooling. So that means anywhere from 14 degrees down to 8 degrees of actual subcooling would mean that you have an accurate refrigerant charge level. If you have higher than 14 degrees, so say you have 15 or 16 degrees, and that would mean that you're overcharged. If you have maybe 5 degrees of actual subcooling, that would mean you're undercharged because you don't have enough subcooling. But anyway, now that we know that we have the correct refrigerant charge level, we also need to look at the blue low side gauge to make sure that the thermostatic expansion valve is actually doing its job properly. We have the blue gauge attached to the large vapor line, and we're measuring a pressure of 114 psi. We convert that to the R410A saturated temperature of 38 degrees. And that's the temperature in the middle of the indoor coil. As the refrigerant flows out of the indoor coil and travels back over toward the outdoor unit, we're also going to take a temperature measurement on that large vapor tube. And there we measure 50 degrees. In order to determine the total superheat, we take 50 degrees minus 38 degrees, and we're left with 12 degrees of total superheat. So a TXV should be able to hold the superheat at the indoor coil between, say, 8 to 14 degrees of superheat. So we're measuring 12 degrees of superheat, so that TXV is doing its job properly. The TXV is good, the refrigerant charge level is good, and so that's the end of scenario 1. Now we're going to move on to scenario 2. I'm going to go over the measurements, I'm going to pause the video, let you solve this for yourself in order to determine if it's undercharged, correctly charged, or overcharged by looking at the subcooling. And then after that, I'm going to explain the answers. In scenario 2, we have the red gauge connected to the small liquid line, and we're measuring a pressure of 376.2 psi. If we were to convert that to the saturated temperature of R410A in the middle of the outdoor coil, we have 112 degrees Fahrenheit. We also have 92 degrees on the small liquid line. Now we also take a look at the blue gauge, which is connected to the large vapor line, and we are measuring a pressure of 118 psi. We convert that to an R410A saturated temperature of 40 degrees, and on the large vapor line, we have a temperature measurement of 50 degrees. We know the job of the TXV is to hold the superheat between 8 and 14 degrees, and we also know that the target subcooling for the outdoor unit is listed as 11 degrees. Now go ahead and solve this problem. On the red gauge, we have a saturated temperature of 112 degrees. We take 112 minus 92, and we're left with 20 degrees of subcooling. So we know our target is 11, and we actually have 20 degrees. We know that we are overcharged because our subcooling is too high. Over on the blue gauge, we have a saturated temperature of 40 degrees. So to determine the total superheat, we take 50 degrees minus 40, and we're left with 10 degrees of superheat. So the TXV is doing its job properly, even though we're overcharged. So because we're overcharged, we're not going to be running in an electrically efficient manner. Now let's move on to scenario 3. In scenario 3, our red gauge is connected to the small liquid line, and we're measuring a pressure of 318.5 psi. We convert that to an R410A temperature of 100 degrees. We also have a measurement on the small liquid line of 97 degrees. Over on the blue gauge, which is connected to the large vapor line, we're measuring a pressure of 114 psi. We convert that to the saturated temperature of 38 degrees. We also have a measurement on the large vapor line of 55 degrees. So in this scenario, first determine if you're undercharged, correctly charged, or overcharged using the subcooling method, because this system has a thermostatic expansion valve. And then after that, look at the implications on the total superheat because of the charge level. I'm now going to pause the video. So in scenario 3, on the red gauge, we have 100 degrees as our saturated temperature in the middle of the outdoor coil. We have 97 degrees on the small liquid line. So we take 100 degrees minus 97, and we have 3 degrees of subcooling, which is very low. That means that we have a low refrigerant charge. Now we're going to look at the blue gauge, where we have 38 degrees as our saturated temperature, and we have a vapor line temp of 55 degrees. So to determine the total superheat, we have 55 minus 38, and we're left with 17 degrees of total superheat, which is a little high. So what we notice is because the subcooling level is very low, the TXV is not able to do its job properly and has a slightly higher total superheat. So we're undercharged on refrigerant in this scenario. In scenario 4, our red gauge is connected to the small liquid line, and we're measuring a pressure of 291 psi. We convert that to a saturated temperature of 94 degrees. We also have a liquid line temperature of 94 degrees. Over on the blue gauge, which is connected to the large vapor line, we're measuring a pressure of 101 psi. We convert that to an R410A saturated temperature of 32 degrees, and we also have a vapor line temperature of 56 degrees. First determine the refrigerant charge level using the subcooling method, and then after that, look at the implications on the low side blue gauge and the total superheat. I'm now going to pause the video. On the red gauge, we have a saturated temperature of 94 degrees, and we have a liquid line temperature of 94 degrees. So we take 94 minus 94, and we're left with 0 degrees of subcooling. So we are severely, severely low on refrigerant. Then we're also going to look on the blue gauge, and we have a saturated temperature of 32 degrees in the middle of the indoor coil. And then we also have a vapor line temperature of 56 degrees. So we take 56 minus 32, and we're left with a total superheat of 24 degrees. So we know that the thermostatic expansion valve cannot control superheat because it does not have a solid column of liquid going to the TXV. We have no subcooling, which means we do not have fully liquid refrigerant heading to the thermostatic expansion valve in order for the TXV to control the refrigerant flowing through it. And because we have a saturated temperature at the indoor coil of 32 degrees, we know that any condensate that's forming from the humidity in the air crossing the coil, that condensate is going to freeze onto that coil, and it's going to turn into a solid block of ice as that saturated temperature continues to lower. And so you're going to have a big problem. So you have a frozen evaporator coil, then you have the TXV cannot control the superheat. You also have no subcooling. You are severely, severely low on refrigerant. And in this case, you need to search for a leak. You would not just add refrigerant into the system. You would have to determine where the leak is in order to then fix it. If refrigerant was added into this, it's just going to end up venting into the atmosphere, which is not good. And then also, the service technician is going to come back again because the refrigerant is just going to leak right back out of the system again very quickly out of that refrigerant leak location. And if you want to learn more about checking the refrigerant charge, make sure to check out our Refrigerant Charging and Service Procedures for Air Conditioning book. We also have a 1,000-question workbook. We also have polystyrene quick reference cards. These can be used out in the field. You can throw them right in your service bag. They're real durable. You can measure the refrigerant charge, check delta T. It goes over refrigerant weights. It goes over troubleshooting indicators for if you're running into a problem. So check all these out over at Amazon and also at our website at acservicetech.com. Hope you enjoyed yourself. We'll see you next time at AC Service Tech Channel.